This is the 15th lecture, problem session 4 on mid-band analysis of amplifiers. As I had commented last time, we would may have a brief discussion on the common drain amplifier, the CD, before we take up problems. Common drain amplifier, and the circuit is very simple, VDD. Then you have no resistance here, at least for AC, common drain, therefore D should be virtually connected to ground as far as AC is concerned, and obviously the load is to be on the source, that is R sigma, and from here you take the output RL. This is V0 and this current is I0. To bias the the gate G, we have two resistors as usual, R2 and R1, and the input is applied here through a capacitor C1, coupling capacitor C1 to the source of resistance RS and voltage Vs. This is the common drain amplifier, and obviously the voltage here is Vi, and it is this gain V0 by Vi that we are interested in. If we know this gain, then we know the current gain. We have to calculate I sub I. We know the current gain, we can calculate the input resistance, and also we have to calculate the output resistance, but V0 by Vs, that is AVs, can also be found out. Okay. The equivalent circuit here, if you go step by step, RS, Vs goes to ground, then we have the parallel combination of R1 and R2, which will be RG, as we have already called it, R sub G, and this voltage is V sub I, this current is I sub I, and then this is the gate terminal. The drain is connected to ground, so the source terminal will now act as the load, the output terminal R sigma, then RL, this is V0 and this is I0. In addition, from the drain to the source we shall have a current generator. The drain is grounded from the drain to the source, so it would be in this direction, and the value of the current generator would be Gm times VGS, and VGS is this voltage plus minus. Okay, this is the story as far as the equivalent circuit is concerned. But don't you see that VGS, is this direction clear? The direction of the current generator? Current generator is from the gate, is from the drain to the source. The drain is grounded. I should have actually drawn a drain here and ground that, but the drain now is grounded, so from ground to the source. Okay, this is GM VGS.
So in that case, in case of common collector amplifier, the direction of IC is opposite to the conventional amplifier.
No, it was the same. The GM V pi had come from ground to the emitter. It's the same. You see, you have to remember that our equivalent circuit is VGS, GS, and then you have the GM VGS here, GM VGS. Now S, D is grounded, so from D to S, that's why this is taken care of. You also notice that VGS is nothing but VI minus V0, isn't that right? VGS is VI, VG minus VS, VG is VI, and VS is simply equal to V0. Okay, that simplifies the analysis, because you see that if I write the node equation at source node, then I have V0 divided by RL parallel R sigma. This is the current going through the parallel combination of RL and R sigma. Then current going out and the current coming in, so this must be minus GM VGS. This should be equal to 0. Okay. The current through here V0 by RL, current through here V0 by R sigma, and the current coming in, that is GM VGS. But VGS is simply VI minus V0 equals to 0, and to maintain uniformity you can write V0 GL plus G sigma plus GM V0 equal to GM VI, and therefore the voltage gain AV, which is simply V0 by VI, would be equal to GM divided by GL plus G sigma plus GM. Obviously this is less than unity as expected. In the common emitter amplifier it is less than unity, so in the common collector amplifier it's less than unity. This is like a source follower, exactly like the emitter follower. It's less than 1, but if GM is much greater than these two, the combination of these two, then it's approximately 1. Okay, so this is also a buffer circuit. Now as far as the input impedance is concerned, you can see that the input impedance is simply Rg, right? Input impedance is simply equal to Rg. So R sub I equal to Rg, and A sub I, which is equal to AV times Ri divided by RL, would be simply GM Rg divided by GL plus G sigma plus GM multiplied by RL. Okay, it must be dimensionally correct. It's a dimensionless quantity. However, to find out the output impedance, you have to make a little more thought. Now, as far as the output impedance is concerned, what we have to do is to make Vs equal to 0. If Vs, if the source is equal to 0, then what is Vi? 0. Vi is 0, and therefore the equivalent circuit becomes GM, I beg your pardon, the direction is wrong. We should have GM Vi minus V0. Vi is 0, therefore minus V0. Agreed? This goes to ground. Then we have R sigma. What else? No RL. We could include, pardon me? RD. We could include RD. We did not include it there, but RD comes in parallel. We could include RD also. In the equivalent circuit drawn earlier, we had ignored RD. If you so desire, you can include this. Let me show you this slide. In this, RD comes from drain to source, and therefore you could include RD, and wherever there is a parallel combination of R sigma and RL, you could include RD also. It doesn't take any extra effort to do that, and I didn't do it by not intentionally, by mistake. Okay, I should have done it. So this is the impedance. Now if you notice, this is my V0 and this is the current I0. I0 will be the sum of three currents, one through RD, one through R sigma, and a current minus GM V0. Now isn't this equivalent to a current which is going out equal to GM V0, right? Agree? I am simply changed the direction. Now a voltage V0 exists across a current generator whose current is GM V0. So isn't this equivalent to simply a resistance of value 1 by Gm? So you can ignore this too. So I didn't write any equation, this is simply by inspection, and that is the strongest tool that an engineer has, common sense and inspection. Inspection, don't take it in the civil engineering sense, it is observation, and there is a difference between seeing and observing. Okay, I will illustrate this later with reference to Sherlock Holmes someday, not today. But if you look from here, isn't it clear that the output resistance will be simply the parallel combination of RD, R sigma and 1 by Gm. Agreed? Without any calculation, any further calculation, I write RD, R0 equal to RD parallel R sigma parallel 1 by Gm. Okay, and our calculations are complete. I must point out here that in order to make a proper biasing of the amplifier, one might be constrained to use a resistance here. One might be constrained, exactly like the emitter follower, you might be constrained to use a resistance here. If you do that, then obviously what you have to do is to correct the AC distortion by using a CD to bypass this resistance. Is that clear? Okay. If we take the same example that we had taken earlier, same example in which your R1 was 1 meg, R2 was 150K, RD equal to R sigma, RD now has to be bypassed, R sigma equal to RL equal to 15K, that is the value that we took. IDSS was taken as 10 milliamps, VP was taken as minus 5 volt, and under these conditions we need something more. What else do we need? No. VDD, that was 15 volt, and under these conditions we found GM as 0.8 millimho and RD was given as 100K. If we make these calculations, please do correct the formulas by including small r subscript small d everywhere that RL parallel R sigma has occurred. If you do this calculation, you get A sub V as 0.85, it is less than 1 as expected. The input resistance is simply the parallel combination of 1 meg and 150K, R1 parallel R2, and that comes out as 130K. The current gain comes out as 7.4, which is simply AV multiplied by RI divided by RL, and this value 7.4, it has become greater than 1 because RI divided by RL is greater than 1. Okay, and R0 is 1.14K. All right. Now we are prepared to work out some examples, some problems. I must point out some of these problems will require the consideration of 2 or more devices, that is 2 or more stages of amplification. Usually what one does is, if you cannot obtain the required gain from a single stage with appropriate input and output impedances, then you use multiple stages. For example, if you have a source of resistance, let's say 1000 ohms, and a load which is 50 ohms, and you want matching, obviously if you use a common emitter amplifier, if you use a CE stage, the output impedance of a CE stage is equal to RC, alright. It would be approximately a K or so, which cannot match 50 ohms. So what you do is you follow a CE stage by a CC stage, okay. You follow a CE stage by a CC stage whose 1 by Gm is equal to 50 ohms. Alright, so matching is performed. The second stage does not give you voltage gain. So the voltage gain has to be obtained from CE, but you match by a CC. Alright, there is current gain in CC as well as CE, and therefore there is an overall power gain. So stages often have to be cascaded, that is, one feeds into another amplifier to get a higher gain or to get a matching, and in such cases, suppose we have amplifier 1 and amplifier 2, okay, and you know that all amplifiers are usually grounded. Suppose we have a two-stage amplifier, alright, then to calculate the overall performance of this is V0, this is Vi. Let's call this voltage as V1. Let's call this voltage as V01, alright, output voltage of 1. Then so long as V01 is calculated by taking the input resistance of stage 2 into account, okay, the effective load of stage 1 would be its own load paralleled by the input resistance of stage 2. If that is taken into account, and you see V01 now acts as the source to amplifier number 2, therefore it is obvious that the overall gain S of V would be the product of the two gains, AV1 times AV2. Alright, this is true provided your effective load RL1 is equal to RL of the first stage, which may be simply RC, paralleled by the input resistance of stage 2, that is Ri2. If you do that, then obviously the gain will be the product of the two. Let's take an example to illustrate this point. Please try to draw with me, because it's a quite involved circuit and it's a practical circuit. Okay, we have a source which is 1K Vs. The coupling capacitor tends to infinity. The first stage is biased by 1 meg resistor in parallel with 220K. This goes to the base of the first stage, Q1, and the first stage has an emitter resistance of 1K, which is bypassed, CE, this is C1, and the load of the first stage is 10K. Okay, this is taken to a plus 12 volt battery. This is the first stage. The output of this is taken without a capacitor, directly coupled to a second stage. This is intentional that this voltage VC1 shall act as VB2, I beg your pardon, VB2, to supply the necessary base current. Let us see if it works. You might, in circumstances, you might overdrive Q2. If you overdrive Q2, Q2 will go into saturation. Once a transistor, a BJT, goes into saturation, it cannot act as an amplifier, and therefore we must caution, we must guard against this. On the other hand, for an FET we require the transistor to be in saturation. Okay, the differences must be quite clear. Now this stage is a common collector stage. It's an emitter follower. There is no resistance in the collector, so obviously it is being used to reduce the output impedance. Okay, it cannot give voltage gain, it simply reduces the output impedance, and this resistance Re2 is 1K, and there is a coupling capacitor, and the load is simply 100 ohm. It could be a combination of loudspeakers. Load is simply 100 ohms. 100 ohms obviously could not be coupled to 10K. That would have been a perfect mismatch. No voltage, absolutely 100 divided by 10K plus 100. This would have been the potential division, and therefore you would have got nothing in the load. But because of the common collector stage, because of the emitter follower, you do get almost the whole voltage, because the voltage gain is unity, almost the whole voltage in the load. The only thing that restricts it would be the output impedance of the second stage, which as you know is low, 1 by Gm. Alright. Now the question is, this is the total story. Beta is given at 80 at 25 degrees C. Beta is given at 80. The questions are the following. First is, find the Q points of Q1 and Q2, that is IC1 and IC2, VCE1 and VCE2. That will determine the Q point. That will also determine whether the transistors are in the active region or not. Okay, this must be checked. And then Gm and R pi for each transistor, Gm and R pi for each transistor, and also the overall voltage gain. This is V0 and this is Vi. You see, if you know V0 by Vi, then you know V0 by Vs also, because you have to calculate, all that you have to calculate is the input resistance of stage 1. Now I shall call it Ri1, alright. And Ai, that is I0 by I sub I. Do you see why I write I sub I before the capacitor? Because after the capacitor there is a DC component. Okay. Could I write I sub I here? Here?
Yes.
Yes, of course. Because DC flows like this. DC flows here. It cannot flow via the capacitor. So it's the same current here. But I cannot write it here, because that contains a DC component. Alright. Now let's look at this circuit carefully and do a step by step calculation. This is a discipline that one has to follow. You might be smarter to guess the results, but my advice would be, do not do this, at least to start with. Okay, you can afford to do this when you are a master in when you have completed a CDS course on analog electronic circuits. Okay, not at this stage. There are too many slips in between. Okay, now let's proceed stage by stage. The first thing we do is to find VBB 1. For the first transistor, VBB 1 would be 12 multiplied by 220K divided by 220K plus 1 meg. So 12 multiplied by 220K divided by, if you want, you can write it as 1000K, 1 meg plus 220K. You must take care of the dimensions, so many volts, and this comes out as 2.16 volt. I have calculated up to the second place of decimals till I felt sleepy. Okay, then I leave out the calculation for the students. Next thing we find out is RB1. Which our aim is to find IB1 and then IC1 and then VCE1. So this is the discipline one is to follow. RB1 is 1 meg parallel 220K, and this is 180K. Nice figure. Therefore 2.16 VBB1 would be equal to IB1 multiplied by 180K plus, this is IB1 times RB1 plus 0.7 plus beta plus 1 is 81 times RE1, that is 1K, times IB1, in which the only unknown is IB1, and therefore you can calculate IB1 as equal to 5.6 microamps, and therefore I sub C1, since ICBO is not given, we neglect it. Okay, therefore I sub C1 is beta times this, that is 80 times 5.6 microampere, which is equal to 0.45 milliamps. The current is small, 0.45 milliamps. But let's not be worried. Let's see what is VCE1. VCE1 is 12 volt VCC minus 0.45 milliamps multiplied by, that is 11K. Okay, and that comes out as 7.1 volt. That's too good. That's pretty good.
Excuse me, sir.
Yes.
Don't we take? Yes, sir.
Yes.
Are we neglecting IB2?
We are neglecting IB2. That's right. You see, in this 10K, it's a very legitimate and valid question. In this 10K, the current that flows is not only IC1 but also IB2. With a beta of 80, we ignore that, and therefore I must put an approximate sign here. I must put an approximate sign here. Okay, because of this ignoring IB2 component. Now 7.1 volt is a good operating point. 7.1 volt, 0.45 milliampere is a good operating point. It's neither too close to 12 nor too close to 0.2. Alright, so this is perfectly alright. And before we leave this, why don't we also find GM1? GM1 is IC1 divided by 26 millivolts, so 0.45 milliampere divided by 26 millivolt, and that comes out as 17.3 millimole. 17.3 millimole, and therefore R pi 1 is equal to beta divided by GM1, and that is equal to 80 divided by 17.3 K, and that comes out as 4.622 K. Alright, first transistor has been exhausted. Everything is known about the first transistor. Now take Q2. For Q2 to calculate the base current, let's go back to the circuit. You see, this current is IC2 plus IB2. Now since we have IC1 plus IB2, correct. Since we are calculating IB2, let's not ignore IB2 anymore. Okay, we can't. Since we are calculating it, well, it's a small part of IC1, but still let's not ignore it. Okay, and this is IB2 as far as DC is concerned. Then we have a 0.7 drop, and then we have beta plus 1 times IB2 times 1K. Therefore, it's not too difficult. What I do is I write 12 volt, that is the VCC, as equal to RC1 IC1 plus IB2 plus 0.7 plus 81 times IB2 times RE2, which is 1K. Actually, I should have substituted values. This is 10K. IC1 we have already found out 0.45 milliamps approximately. Therefore, everything is known in this equation, and I get IB2 as equal to 74.7 microamps. And if IB2 is 74.7, obviously IC2 okay, IC2 would be equal to 80 multiplied by 74.7 microamps, and that comes out as 5.98 milliamps, approximately 6 milliamps. And under this condition, VCE2 would be equal to 12 volt minus 1K multiplied by 5.98 milliamps. That is approximately 6 volts. 6.02, ignore 0.02.
Excuse me, sir.
Yeah.
Sir, in that two calculations involving VC1, the two are different by about 0.7 volts, because in the first case we have ignored IB2, and the second one we are considering IB2.
Say it again. In the second case,
So when we are calculating IB2,
that's right.
then IB2 comes out to be 74.7 microamperes.
Correct.
This will make a difference of about 0.7 volts in VC1 because it's flowing through 10K resistance.
That is correct. That is correct. Let me see. 74.7 microampere multiplied by 10K. How much is that? 0.7. Yes, that will make a difference. Yes. Quite correct. So, what is different in VCE1? Does it affect GM?
Yes, sir.
VCE1? No. It's I sub C1 divided by. But then I sub C1 will also be different, slightly different. So these are all approximate calculations, all approximate, and they keep life simple. If you have to consider IB2 also, well, it will be a coupled equation, a set of coupled equations. You have to solve them simultaneously. And an engineer doesn't want that. And the reason is, whatever you do, after all, when you get a 1 point, you see one of the resistances here is, let's say, 4.622. Where do you get, if you go to the electrical engineering store and ask him, give me an exactly 4.622 kilo resistance, he will say, sorry, okay, so final values, they cannot be put exactly. Now, if you are too fussy, then you have to take, let's say, a dozen of 4.7K resistors, and hopefully one of them will be 4.622. If it doesn't come, well, the approximate value, 4.6. So this adjustment you have to do. Number two, since these are linearized designs, linearized models, after you assemble the whole circuit, if you are designed for a gain of 100, you may get 98 or you may get 120. Then you have to make adjustments anyway. So in these calculations, design calculations, one need not be too fussy, because in the ultimate fabrication, you do have to tune this circuit. This is what is called tuning. You have to tune this circuit or polish this circuit to match what you want. Okay, that's why. Otherwise, if you had been very fussy and do all the calculations with all the sweat, then you fabricate it and you find that it has not been worth it, because you have to change the resistors anyway. All right. Well, VCE2 and IC2, this is also a good operating point, 6 volt and 6 milliampere. Okay, it's a good operating point, and we can now calculate GM2, IC2 by 26 millivolt. This comes out as 230 millimole, and therefore R pi 2 is equal to beta divided by 230 so many K, and this comes out only as 348 ohms. 348 ohms. It's a low value. Why does this low value arise? Because the current is much larger. It's 12 times larger, right? 6 milliamperes. It's 12 times larger than IC1, and therefore R pi 2 correspondingly goes down. Now, to calculate the gain, what I should do as a matter of discipline is to draw the equivalent circuit. But let's try to do it by inspection. Okay, just by inspection. The gain of the second stage, you have to start from the last. Why? Why? You cannot start from here unless you calculate Ri2. So you start from the last. AV2, this is a common emitter, common collector amplifier. So it would be, the gain would be, GM multiplied by the parallel combination of RL, RE and 1 by GM. No R0 comes here. R0 can be ignored because these are small resistances. If you recall, the common collector amplifier, AV2 is GM2 multiplied by RL2 parallel RE2 parallel 1 by GM2, and this is approximately equal to unity. This comes out as 0.95 in this case. We know GM2, we know RL2, RE2 and 1 by GM2. This comes out as 0.95, which is pretty good. Okay, and under this condition Ri2, that is the input resistance of the second stage, let's see what this shall be. It would be R pi 2, okay, from here to here, plus beta plus 1 times the effective load here, that is 1K and 100 ohm. Okay, so Ri2 is R pi 2 plus beta plus 1 times RL2 parallel Re2. I am doing this by inspection without drawing an equivalent circuit. Okay, and this comes out as 7.7K. This is a high enough resistance. Okay, 7.7K. And if I know Ri2, then the voltage gain of the first stage, Ri2 is here. Therefore, the effective load of Q1 shall be 10K parallel Ri2. Okay, so the gain of the first stage would be minus GM. Pardon me? Oh, I want to find out the gain of Q1, and the effective load of Q1 is 10K in parallel with what it faces from the second transistor, that is Ri2, this resistance, and this resistance I had already calculated as 7.7K.
How is that in parallel?
How is that in parallel? From this point to ground I have two paths, one is 10K and the other is through this. Okay, so the the gain of the first stage would be minus GM. Notice there is a negative sign, it's a common emitter stage, there is an inversion, minus GM1 RL1 parallel Ri2, this is 10K and this is 7.7K, and this comes out as minus 75. Okay, minus 75. Approximately. You see that my second place of decimal is gradually disappearing. Okay, I must also find Ri1 to know completely about the amplifier. What is Ri1? Ri1 is Rb1, okay, parallel R pi 1. Anything else? No, this is bypass, this 1K is bypass, so no beta plus 1, it's simply Rb1 parallel R pi 1, and that is 180K parallel 4.622K, and that comes out as 4.5K. Why do I need this? I need this to be able to calculate AVS. AVS is now, but I have not calculated AV yet. The total voltage gain is simply the product of AV1 and AV2. So minus 75 multiplied by 0.95 minus 71.5, and A sub I is AV, that is minus 71.5 times Ri1. This is why I declare Ri1. 4.5K divided by RL. What is RL? Overall RL, 100 ohm. And this comes out as minus 3217. And finally, you can calculate A sub V. A sub Vs as equal to AV, that is minus 71.5 times Ri, that is 4.5K. So 4.5K plus 1K. And I didn't calculate it for obvious reasons. Okay. Second problem. Is the problem clear? It's a fairly involved design, it's a fairly involved analysis, but if you keep your eyes and ears open, you can do it almost by inspection. Make sure you don't make a mistake in observing the input impedance of the next stage in the load of the previous stage. As long as you do that, there is no problem. Let's take another example in which in which the second stage is also a CE amplifier, common emitter. And the example is this: 1K Vs C1 1 meg and 1 meg. The two resistors are equal. This goes to Q1 and Q1 1K is bypassed. The load here is 10K and this is plus 12 volt. The load is 10K. Then the output is coupled now not directly but through a capacitor to the second stage Q2, which, since there is a capacitor here, you must bias the second transistor in the usual manner, that is, use a resistance here and a resistance here. Okay, I am not supplying from the output of Q1 a DC, and therefore I must supply from the power supply. These resistances are 100K and 22K. The emitter of Q2 goes to ground via a resistance of 100 ohm and which is bypassed, C5. The other capacitors are C1, C2, C3, C4. This capacitor is C5, is named C5. Why it is being named, I'll come in a moment. The load, the R sub C of this transistor Q2 is 1K, and this capacitor is a coupling capacitor, and the load is 1K. This is my V0 and this is I0. The problem is, it's a fairly involved problem, but we will solve it. The problem is to find out first Q points. Beta is given as 100. Beta is given as 100 for both the transistors. You have to find out the Q points and GM and R pi for each transistor. That's routine. You must do it the same way, except that you have to calculate IB here from VBB2 and RB2 for the second transistor. It was not required in the previous case, but it is required here. Okay, GM and R pi. Then you find AV and AI for two cases. One is for C5 tends to infinity, which means that it is bypassed. This 100 ohm is bypassed, and the other is C5 tends to 0. That means it is not bypassed. All right. If it is not bypassed, if C5 is 0, roughly what will be the voltage gain of Q2? Can you, just by looking at it, can you tell me what will be?
10.
No. Sorry. Do you understand the question? The question is, if C5 is 0, if it is not bypassed, what will be approximately the gain of this stage?
5.
5 is the correct answer. It is -5. Negative of effective RL, 1K and 1K come in parallel, 500 ohms divided by RE, which is 100, so 5. You should not expect a gain greater than 5 from here if C5 tends to 0. Okay. Now let's see, let's solve this problem stage by stage. Since these calculations are routine, I will simply write VBB1. It is obvious that it is equal to 6 volt, 1 meg and 1 meg, and RB1 obviously it is 500 K. All right. So 6 would be equal to 500 K times IB1 plus 0.7 plus 101 multiplied by 1K multiplied by IB1, which gives you, nevertheless, if you do not understand this step, please stop me and tell me to repeat or to explain, okay? IB1 is equal to 8.8 microamperes. Therefore, I sub C1 is equal to 0.88 milliampere. Multiply this by 100. And therefore, VCE1 would be equal to 12 minus 0.88 milliampere multiplied by 10K plus 1K, so 11K. And this becomes equal to 2.3 volt. That's not too bad. Then GM1 would be 0.88 divided by 26, and that becomes 34 millimole. And R pi 1 therefore beta 100 divided by GM1, and that comes as 2.941 K. Alright, so far so good. Any question? Before we go to the equivalent circuit or calculation of gain, let's find out for the second stage also. VBB2 now becomes 12 multiplied by 22 divided by 122, right? So many volt, and that becomes equal to 2.16 volt. RB2 is equal to 100K parallel 22K 18K. Good figure? So 2.16 is equal to 18K multiplied by IB2 plus 0.7 plus, yes, now 101 multiplied by, can you say 1.1K? Right? 1.1K, 1K and 100 ohms. 100 ohms is 0.1K, I hope. Right?
So how does 1K come into picture?
1K is here. 0.1K. It cannot be 1K. It can be 1.1. We are not calculating VCE2. That's where 1.1. But this is 0.1. Simply that 100 ohms comes into the picture. Okay. And that gives me IB2 as equal to 52 microamps. Therefore, I sub C2, which is multiplied by 100, is 5.2 milliamps. And then GM2 is 5.2 divided by 26, very nice figure, that is 200 millimole, and R pi 2, which is 100 divided by 200 millimole, is obviously 0.5 K, that is 500 ohms. All done? Now we are ready to calculate the gain. Okay? Now, in calculating the gain, let's look at the circuit again. I am not drawing another equivalent circuit. If you so desire, you may draw it, but the gain of second stage, last stage, Q2, if this is bypassed, then the gain would be minus GM2 multiplied by the effective load, which is 1K parallel 1K. Yes.
So we have not calculated VC2, which is quite close to 12.
Okay, great. I was expecting this question. VCE2 is equal to 12 minus 5.2 milliampere multiplied by 1.1 K. How much is this? 6.3 volt. This is not low. This is okay. So we are in business. Alright, now let's look at the gain of the second stage. Obviously, the effective load is 1K parallel 1K, 500 ohms, and GM2 multiplied by GM2. So, AV2 is equal to minus GM2 RC2 parallel RL2, and that comes out as minus 100. 200 millimole and 1K parallel 1K, 0.5. Okay. So, This is, the gain is minus 100. Then the next calculation is, I must calculate Ri2. I must calculate Ri2. This would be parallel combination of 18K we have already calculated, RB2. Okay, so 18K parallel R pi 2, if this is bypassed. Okay, so Ri2 is 18K parallel, how much? That is 500 ohm. And that comes out as 486 ohms. The reason I shifted is, instead of writing 0.486K, I write 486 ohms. Okay. Therefore, now we can calculate AV1. AV1 would be minus GN1 multiplied by the effective load 10K parallel 486 ohms. Will become quite low. And this comes out as minus 15.8. Therefore, AV would be minus 100 multiplied by minus 15.8, and that is 1580. Okay. C5 is bypassed, yes. We will see what happens when C5 is not bypassed. Okay. So this is my A sub V, the voltage gain. Then I require to calculate the current gain, we require Ri1. Ri1 would be equal to, yes, RB1, which is 500K in parallel with R pi 1, that's all. What is R pi 1? 2.94K, and that becomes 2.92K. Therefore, you can calculate AI, which will be 1580 multiplied by 2.92 divided by 1. So this becomes 4600. Very good. Two stages have achieved this much of current gain, 4600 times. And finally, well, you can calculate AVS. What would be R0? What would be R0 for this amplifier? Yes? Output resistance. I mean, 1K parallel. No, don't make this mistake. It is the resistance. No GM, no 1 by GM. 1K parallel, if you want to parallel it with something, it would be small r subscript small o, not GM, because this is a common emitter amplifier. Okay, but if you ignore that, don't make this mistake of 1K parallel 1K, because the load now sees, therefore load is the master. You can't absorb the load in R sub C, no, it refuses, because you are calculating what the load sees. Alright, so R0 is 1K. If we ignore small r0, and the you can calculate AVS as AV multiplied by Ri divided by Ri plus Rs. Now the second part, that is, if C5 goes to 0, then the voltage gain of the second stage AV2 reduces drastically. It becomes minus GM2 RC2 parallel RL2. This is divided by 1 plus GM2 times RE2 if C5 tends to 0. Stands to reason if RE2 is effectively 0, then it is simply this gain. So the gain is divided by 1 plus GM to RE2, and you can verify that this figure is 20. This is 20 here. So the voltage gain is reduced 21 times, and this becomes minus 4.76. What did we calculate roughly? Minus 5. So it's not too different. Agreed? It has come down. The input resistance of the second stage would now be RB2 parallel R pi 2 plus beta plus 1 times RE2. If you calculate this, it increases to 6.7K. It increases. AV1, do you expect it to increase or decrease? RI2 has increased, and therefore its effective load has increased, and therefore AV1 it's increased. It becomes minus 136. I mean the value. Take account of the inversion later. So it has increased, but lo and behold, AV, which is the multiplication of these two, is 647. It has decreased. Previously it was 1580. Okay. And A sub I, you can calculate, A sub I is 1889. This has also decreased. This has also decreased. But the output resistance now, what is the output resistance? Does it change? It is the same. It is the same as 1K. Alright? And that completes the calculation of a fairly involved two circuits. The ones that are set in the tutorial class will be much simpler. I think this is a point where we can close the class.